right, what we're talking about today is the introduction to something called intermolecular forces, and that goes along with the idea of polarity. And both of these things were introduced really briefly in that video that you watched last week. Intermolecular forces are the forces that occur between molecules, like an international flight goes between countries. And when we talk about the forces in between molecules, we need to understand a couple of things about that molecule first. So we already know how to figure out what dot structures look like, what the shape would be. What we're going to talk about today is narrowing down a little bit more what kind of bonds that molecule has, and then combining that with the shape to figure out kind of overall what sort of molecule are we going to get. So first of all, we need a couple definitions. Some bonds are called polar bonds, and sometimes you will see this listed as polar covalent bonds. So we're talking about covalent bonds here. It's one specific type of those. Polar covalent bonds, or just polar bonds, are those where the electrons, or the shared pair, are shared unequally. You determine whether or not a bond is polar by looking at the atom's electronegativity. We talked about electronegativity last semester when we talked about the periodic table. Just as a reminder, the electronegativity is the attraction that an atom has for the electrons in a bond. So if you have two atoms that are sharing electrons in a bond, which of those atoms wants the electrons more? Or which of those atoms has the electrons attracted to it more? The electronegativity is the number that tells you that. The more electronegative of the two atoms gets more of the electrons. Another way to say that would be that the more electronegative atom has the electrons being closer to it. It's got a stronger attraction for those electrons. The electronegativity numbers, or the scale, is just an arbitrary scale. Fluorine is the element or the atom with the highest electronegativity. So somewhere along the line, somebody designated that as 4.0. That's going to be the highest electronegativity that there is. And everything else is based off of fluorine. So everything else will have a smaller number than that. These are in, I think, the lower right-hand corner of the boxes on your periodic table. And you are going to have to use the one on the back of your packets for this one. I don't know if I put it on this packet. Did I? Yeah, you've got a periodic table there. The one in your planner does not have electronegativities on it that I know of. So let's look at an example. If we have a bond between hydrogen and chlorine, this is hydrochloric acid. You could look up the electronegativities for both of those elements. You just look it up on your periodic table and find out that hydrogen's electronegativity is 2.1 and chlorine is 3.0. which of those atoms are the electrons going to be closer to? The chlorine, because it's got the higher electronegativity. So if the electrons are closer to the chlorine, that means they're further away from the hydrogen. And that causes this bond to be polar, meaning that it has a plus end and a minus end. Because what charge do electrons have? Negative. So if all the electrons are hanging out on one side, that side's going to be kind of negative. And what does that leave the other side to be then? Positive. You can show that a couple of different ways. One is with an arrow that's kind of got its tail turned into a plus sign. The arrow points towards the more electronegative element, and then the plus sign on the tail tells you what side would be kind of positive. So that tells you the chlorine is kind of negative because that's where all the electrons are. The hydrogen is kind of positive. And here's that little explanation here. Chlorine is more electronegative. So that means the electrons are closer to the chlorine, which in turn makes that side slightly negative in charge. There's another way that you can show that, and that's with a Greek letter. This Greek letter down here, this is a lowercase delta. It kind of looks like an S, or almost like an 8 that you didn't finish. I like that when you draw it by hand. The lowercase delta tells you that there is a partial charge on that side of the bond. So chlorine is partially negative, hydrogen is partially positive because of where the electrons are. So the lowercase delta means partial charge. So when you're looking at electronegativities, when you're looking at combinations of different atoms, how do you decide if the bond is going to be polar or not? What kind of bond is it going to have? There's a scale, or kind of like a chart, that uses the electronegativity difference. And I usually abbreviate that END because that's kind of long to write out. The electronegativity difference. What's a difference in math class? What's that mean? Subtract. So we're going to be subtracting electronegativities to figure out what the difference is between them. And then we'll be looking at this scale or this chart. We have 3 divisions on the chart, or 3 categories of bonds. And you will want to draw this chart in your notes. It's pretty simple. You'll be using it on your homework though. So the first division that we have is 0 to 0.4. Any bonds that have an electronegativity difference of less than 0.4 are called nonpolar covalent. They're covalent because the electrons are still shared. They're nonpolar because the electrons are shared evenly or equally between the 2 atoms. right down the middle. An example of something with a nonpolar covalent bond would be Cl2. If you wanted to find the electronegativity difference for Cl2, look up chlorine, and you subtract them. What do you get? 0. Without even looking it up. You don't even need to look that one up because they're the same. So if the electronegativity difference is 0, those electrons are going to be shared right down the middle. That means it's nonpolar. If you subtract and you get an electronegativity difference that's between 0.4 and 1.7, then that's the category that we call polar covalent, what we just went over. The electrons are still shared, but they're not shared evenly. They're going to be closer to one atom than they are to the other. An example of a bond that is polar covalent is the bond between oxygen and hydrogen. That's the kind of bond that occurs in water molecules between oxygen and hydrogen. If you were to find the electronegativity difference for those, you'd look up oxygen, you'd look up hydrogen, subtract them, and it turns out that you get 1.4. If you get an electronegativity difference that's higher than 1.7, that tells you that that bond is ionic. So instead of electrons being shared, there's a complete electron transfer. Something loses, something gains. An example of an ionic compound, example we've used every time we've talked about ionic compounds, is NaCl. If you look up sodium and chlorine and subtract them, the electronegativity difference comes out to be 2.1. One small note that we should make about this chart before we move on. This chart has divisions in it. There's a line. And just by the appearance of the chart, it looks like that line is just a cutoff. 0.4 is it. 1.7 is it. But it doesn't work quite that way in real life. It's more of like a gradient. You know what a gradient is? Like in PowerPoint, if you're going to do a gradient background, what's that mean? Yeah, it kind of distributes. If you do it in PowerPoint, you get to choose like 2 or 3 colors, and one color fades into the next color. You guys have seen these before, yes? Think about a rainbow. A rainbow has a gradient too. It's not just a solid cutoff between the red and the orange. The red just kind of fades into the orange, which fades into the yellow. This chart is more like that. When you get close to the borders, things get a little bit fuzzy. Sometimes it's not so easy to tell whether it's going to be nonpolar or polar. You might even get an electronegativity difference that's right on the border, and then you have to make a choice. When we get to doing a test on this, everything's going to be clear cut for you guys, but I wanted to point that out, that it's not a solid cutoff like we show on our chart. It's more of like a fading of one kind into the next. Okay, so we've talked about different kinds of bonds within the molecule. You could have ionic bonds. You could have polar covalent bonds, or you could have nonpolar covalent bonds. Depending on what kind of bonds you have, and one other qualification, it turns out that you can also have a molecule that is polar or not. A polar molecule is an entire molecule that has a plus end and a minus end. So instead of just having a bond that's polar, you can have an entire molecule that's polar. There are 2 qualifications that you have to check to see if a molecule is going to be polar or not. First, it has to have polar bonds. The bond is what's going to cause those electrons to be on one side or the other. So if it doesn't have polar bonds, the molecule itself is not going to be polar either. The second thing that you have to check is the shape of the molecule. And specifically, we're looking to see if the molecule is symmetrical or not. Those two things can work together to make a molecule overall have a plus end and a minus end. And that's going to be important when we start talking about the forces in between the molecules. Because if you have two molecules that have a plus end and a minus end, they can kind of act like magnets. Pluses and minuses attract. So we have to be able to determine if a molecule is polar to know what kind of forces it's going to have between it and the next molecule over. A molecule is polar if it has polar bonds and it's not symmetrical. The reason we have to check for symmetry is because in symmetrical molecules, the polar bonds will kind of like cancel each other out. The pluses and the minuses would cancel each other out so that it wouldn't matter that the bonds are polar. We're going to do a few examples with this. You'll have to determine the type of bond first, so that'll be practice with that. And then we'll be checking to see if that molecule is symmetrical or not. So we will be drawing some dot structures and line structures as well. We'll start with a simple one, H2. First thing we need to decide is if this is a polar bond or not. You would look up the electronegativities, subtract them. Because the two atoms are the same, what's the difference going to be? Zero. So what kind of bond does this have? Non-polar. The electronegativity difference is 0. That means the bond is non-polar. If the bond is non-polar, we don't even have to check for symmetry because we didn't meet the first qualification. So we know that this is not going to be a polar molecule. Next one, lithium iodide. First thing we have to do is determine if the bond is polar. So that means we need to look up the electronegativity for lithium and for iodine. And subtract them, and you end up with 1.5. The electronegativity difference is 1.5. According to our chart, what kind of bond does this have? Polar covalent. So polar bonds. And then we have to check for symmetry. To decide if this molecule will be polar or not, we have to check to see if it's symmetrical all the way around. There's a couple of ways that you can do that. The one that I like, that works the best for me, is to imagine that I have a mirror, and it's a double-sided mirror. And I can put it wherever I want in the molecule. So if I had a mirror, and I put it right here, do I see the same thing on both sides of the mirror? No, because one is lithium and one is iodine. That means the molecule is not symmetrical. It's not the same thing on both sides. We would call that asymmetrical. If it has polar bonds and it's asymmetrical, that means overall we have a polar molecule. This molecule as a whole would have a plus end and a minus end. Let's do another one. Everyone's favorite molecule is H2O, water. Notice that I drew my picture in the correct shape. We should know now that water is bent or V-shaped, so I drew my picture that way. First thing we gotta check is the bonds. Check for the electronegativity difference. So you'd look up oxygen and you'd look up hydrogen. And I usually get the question here, do we have to double the hydrogens? No. Because we want to determine, is this bond polar and is this bond polar? There's two separate bonds here. So you just need to do the subtraction for each one. It just turns out that because the bond combinations are the same, this is an O and an H, this is an O and an H, the electronegativity difference is going to be the same for both bonds. Does that make sense? But you just have to subtract it once. So you look up oxygen, you look up hydrogen, you subtract. Electronegativity difference comes out to be 1.3, 1.4. Different periodic tables say different things. They round differently. Either way, though, what kind of bonds do you get? Polar, covalent. Because we met the first qualification, now we got to check the second. Is this molecule symmetrical or not? And now we have to use our mirror trick and check a couple of different directions, because if you put the mirror here, right through the oxygen, do you see the same thing on both sides?
Yeah.
Yes. Almost like you could fold up those two hydrogens and they'd match. But if you put the mirror here and looked below and above, do you see the same thing? No. So what you got to realize is that when you're checking for symmetry, it's almost like you got to check every direction. Everywhere that you can think of to put that mirror, or at least in the three main dimensions, you've got to check all those directions. Because if you get one asymmetrical direction, the molecule is asymmetrical. The other way you can check that is with those arrows that I showed you with the positives on the tails. We should recognize that hydrogen would be kind of positive and oxygen would be kind of negative because oxygen had the higher electronegativity. So if you were to draw those arrows, they would point towards the oxygen, like that. And you can check and see which direction the arrows are pointed to. If the arrows are pointed straight at each other or straight away from each other, like head to head or tail to tail, those are going to cancel out because the molecule is symmetrical. If they don't point straight at each other, like here we're almost at 90 degrees, then those arrows don't cancel out. So you can check it with the mirror idea, or you can check it with the arrows. If you get one direction that's asymmetrical, the molecule is asymmetrical. So, at the end of all that, we realize that water is polar. Water has a plus end and a minus end. That's part of what gives water some of its very cool properties, like its surface tension. Water is a pretty strong surface tension because all the molecules will line up like V's kind of next to it because they're like magnets, they stick together. Next one. This was your bell ringer. CCl4. There are 4 bonds in this molecule, but they're all the same. Each bond goes from a carbon to a chlorine. So to check the bonds, we just need to subtract once. And you get an electronegativity difference of 0.5. What kind of bonds does this have? Polar bonds, just barely. And if it has polar bonds, then we need to check for symmetry. So if you're going to do it kind of like with a mirror, check here. Do you see the same on both sides? Yep. Check here. Yes. What if you put it a diagonal? Yeah. The other diagonal? Yeah. Can you think of anywhere that you wouldn't get the same thing on both sides? Not with this one. The other way that you can check that is with the arrows. What are they going to point towards, the carbon or the chlorine? Which one's more electronegative? Should be the chlorine with the higher number. So all of the positive tails would end up in the center, where the carbon is. All of the negative ends, or arrowheads, would be towards the outside. And see here we have 2 and 2. Tail to tail going across and up and down. So those arrows cancel out. That means this molecule is symmetrical. So overall, it's nonpolar. I think we have one more example to do and then we're done. NH3, this is ammonia. There are 3 bonds to check here, but they are all the same. So we just need to subtract once. The electronegativity difference turns out to be 0.9. So what kind of bonds does this have? Polar. If it has polar bonds, then we need to check for symmetry. And again, you can do that with mirrors or you can do that with the arrows. If you had a mirror going right up and down the center, would you see the same on both sides? Yep. What about if you put it here, top to bottom? No. So this one is asymmetrical. The other way you can check that is with the arrows. 2 of them point at each other, so 2 of them would cancel. But because you've got that third one down on the bottom that doesn't have a match, that one doesn't cancel. So we end up with an asymmetrical molecule, which tells us this is polar.